Alright, so this video actually has nothing to do with the mysterious Mazarin, so I decided to make a new title card. Kelly does just whatever, I guess. Something like that. Alright, so we've all been in this same situation playing video games. You're just standing around doing nothing and uh-oh, here come the bad guys. Looks like they're coming to get you. Uh-oh. But how do they know where you are? This is a little area of artificial intelligence we like to call navigation. So by far the most effective way to create good navigation in Unity is to use their built-in NavMesh system. It's pretty simple, the instructions tell you exactly what you need to do, and it's all automatic. So Unity sort of creates a grid of different points, and each point stores how each point is connected to other points on the grid, and that makes it super fast to calculate a path from one point to another point. And that's how the navigation works. Now, a lot of people think that you have to use a NavMesh agent in order to facilitate movement on a NavMesh, but the cool thing about the NavMesh is that you can actually use a NavMesh agent to simply calculate the path, and then you can access the waypoints in that path in a data structure. That means you can use any navigation method you want to navigate the waypoints. So that makes it very powerful. Today I want to talk about a different method though, called Raycast steering. Raycast steering, the agent can't do complex navigation, all they can do is simple obstacle avoidance. So to begin with, we use simple high school trigonometry to create a circle of rays centered around the agent. The number of rays is variable. The more rays we have, the more precise it is, but the more computationally heavy it is, so it's a trade-off. So if we want the agent to chase a certain target, in this case the player, we take a direction vector. We find the direction vector by subtracting the agent's position from the target's position. Next, we loop through our circle of rays, and for every ray, we take the dot product of the direction vector that we computed and the direction of the ray. And the dot product gives us a number which roughly indicates how well the directions align. Here I've color-coded the results so that the greener values are pointing more towards the player and the redder values are pointing away from the player. Well, you may be wondering, if it's so easy to compute a direction vector pointing directly towards the player, the target, then why do we need to fool around with this circle of rays? Why do we need to compute all of these different dot products? Well, the answer is, what happens when our enemy encounters a wall? In this case, let's disqualify that direction ray. Then we have all these other rays to fall back on. But we can still find a different route, even though the optimal route is blocked. We still have alternatives to find a route to get to the player, to get to our navigation target. So you can see how this circle of rays emanating from our navigation agents, it can detect walls, it can determine alternative directions for the agent to go, and that's how it can navigate to the target despite there being obstacles in the way. So it's a simple way to avoid obstacles, to steer around obstacles, and eventually find the target. Alright, so I may have come up with some of the implementation methods myself, but this overall method I did not originate. This is not my original idea, and I got the idea from a video which I will link in the description below. I recommend looking at that. It's got lots of good ideas for artificial intelligence behaviors, which might make your game more interesting, and it definitely inspired me.